Stockholm problem. How much that is? There's a date? How long? I know. I mean, she's really mysterious. Oh, yeah? Okay. Then I will, What's that?
He shows up in the Colloquium.
Let's talk about that stuff. Okay. A boss for HAWC. Hot boss. Interesting.
So you don't need those Geiger counters next week, do you? Yeah, we're good. I just wanted the students to be able to use the same ones. So an undergrad lab we do in one day?
You have 6 if you're using it.
Well, I can do that after
That's fine. I've been here since 1997.
Yes, and then usually this week. Okay.
That's it. And my name, that's all.
Well, that's why you have two for that, so you can go to any of those. So did you, what's his name actually get in there? Yeah.
Center of the multi-way before the
What?
right.
Oh, yeah, I did put it on this. Okay. Yep. I didn't know if we got it.
It's looking
I'm
southeast.
just actually reading through these.
It is looking southeast.
This is southeast, actually.
Drafts of
It's not
abstracts, so.
It's better than what I've seen.
Google Earth isn't perfect.
It's better than what I've seen George Goodman do.
What?
And actually, when it's that low in the sky, it's how we can see it.
That's very good.
Artists-
No, I know, that misses the guy from.
George is coming here on the first and second. CA.
He was an external reviewer, not for the department.
I didn't actually check it out.
I remember interacting with him the first time I was and he was, what was interesting is that he had been a chief partnership. Department chair. At Maryland, he was department chair for a long time. Still is.
He's no longer chair. He should have been president of the university. He started out as an undergraduate.
He's never left Maryland?
Wow, he's been to Antarctica and other places.
Professionally left?
But he's always working on it.
Was undergraduate, graduate, postdoc, and professor.
I don't know why they gave him tenure.
I was undergraduate, graduate, postdoc. So I question if he could do it. I should become
He did send me to talk about
Because we're thinking all the time about
So I put in
ground floor. The computer library. So I have a lecture that I'm giving for the first 30 minutes or so. And then there will be a survey or some students that so you can probably see all first you'll see the
Can I look through a telescope too?
yes, definitely.
Thank you, thank you.
I know I have it.
great idea. Of course, there are many schools because we will have a number of course of these components. Always take the website.
Not with the Newtonian, but those kind of things are one of the ones
Yeah, so there it's a little.
Hello, everyone. Today's speaker is Wayne Sprangin. He got his bachelor's degree and PhD degree both in physics from University of Maryland, and he joined the department in 1997. Before that, he also worked at University of Alberta in Canada for 3 years.
But I was stationed in Switzerland.
And
I spent 7 days in Alberta.
associate professor in 2004, and he has been working at the High Altitude Water Cherenkov Observatory and Frisco Peak Observatory, and also the telescope array. Today you can see that he's going to tell us about his work at the HAWC Observatory.
Okay, so I have 82 slides that will describe what's in this picture. I'm going to start off discussing some background about gamma rays, cosmic rays, and then sort of do a comparison of the various types of gamma ray observatories that exist. There have been many, dozens actually. Then I'm going to go into the specifics of the HAWC Observatory and then share some of the first results. So let's start off in familiar territory. This is the flux of cosmic rays versus energy. And last week, John Bells told you about the activities of the telescope array group, covering this region in here. They are pushing the energy sensitivity downwards to tail. What I'm going to be talking about today covers the range of about sub-TeV to several hundred TeV, TeV astrophysics. We can see cosmic rays, and we can also see gamma rays, and I will show you what the challenges are with that in a moment. In between these areas, there's actually measurements performed by a wonderful, actually several experiments. So all of those energy regions are covered. So I brushed off my recollection of this wonderful software known as PAW and utilized the CUMAC that was produced by Simon Sorty, who made this very famous cosmic ray flux. And I attempted to try to put the flux measurements by Hess of the Crab Nebula. Now, it doesn't really quite make sense to do that because this is a point source, and this cosmic ray flux is measured over the whole sky. But if you were looking at a cosmic ray detector that had one steradian aperture, then this comparison is sort of legit. Anyhow, the point is that if you're going to be looking for gamma rays, you're going to have to deal with a lot of cosmic rays on top of them. Okay? So, the predecessor to HAWC, Milagro, made a measurement of the cosmic ray, of the gamma ray flux from the crab. And one thing I wanted to point out to the cosmic ray experts here is that they actually didn't measure the event energy event by event. They basically used some other observables and modeled the response of the detector to a certain spectral function, and were able to determine the energy spectrum without measuring things event by event. It's kind of a clever technique. So, some further background information about what we're looking at with HAWC. We're principally interested in gamma rays, but we also have about 1,000 times, more than 1,000 times more cosmic rays to look at as well. But the theoretical interest associated with those measurements is to look at what's going on in these astrophysical objects that are accelerating particles to prodigious energies. So, in the acceleration of ultra-energy cosmic rays, it's presumed that there's shock waves and there's all kinds of energetics going on that can also produce gamma rays. So one of the goals of these gamma ray measurements is to look for the source of ultra-energy cosmic ray production. And there's been some progress made along those lines. So how can you get gamma rays? You can get gamma rays in the TeV range through neutral pion production and decay. You can get gamma rays through inverse Compton scattering, where you have a high energy electron scatter a photon to high energies of the order of TeV. Another very interesting means of possibly producing gamma rays is the annihilation of dark matter particles. So this is an artist's rendition of what a spiral galaxy would look like if there were dark matter particles annihilating in these lobes. And actually the Fermi Gamma Ray Telescope has seen some indications that that's actually may be the case for our galaxy. These are known as the Fermi Bubbles. So the physics of compact objects and their relativistic outflows, how cosmic rays originate and propagate through the galaxy, dark matter annihilation. We can study this extragalactic background light, and also we have some sensitivity to studying exotic physics by looking at timing of gamma rays arriving from various phenomena to test Lorentz invariance. We've actually already evaluated the sensitivity of HAWC to detecting black hole evaporation. So if you look at the gamma ray skies, this is the gamma ray sky, the sky seen by the Fermi telescope. You see a lot of activity. That right there is the Milky Way. There's also extragalactic sources. For the lower energy GeV band that the Fermi satellite is sensitive to, there's more than 2,000 point sources. There's also diffuse emission, for instance, the Fermi bubble. In the TeV band so far, I don't know, Dave might be able to update my knowledge on this. There's in excess of about 150 point sources. There's diffuse emission, and one of the strong points of the HAWC Observatory is that it has greater sensitivity to measuring diffuse emission flux than the Rare Cherenkov telescopes, and I'll be going more into that in a few moments. So the HAWC Observatory, as I'll describe, looks at basically 2/3 of the sky as the Earth spins once in a day. Okay? So we are surveying a significant fraction of the sky. So we have a huge potential for finding new objects. So what astrophysical objects might we see? Extragalactic objects such as active galactic nuclei. We have sensitivity to gamma ray burst, although we haven't seen anything yet. Pulsar wind nebula we can study, starburst galaxies, supernova remnants, pulsars, solar flares, diffuse emission, lots of things. In gamma rays, you can see the arrival direction, so you can actually see objects, unlike where I was coming from in cosmic rays, although there's claims that they're seeing objects now. So active galactic nuclei, there's models that I won't go too much into, but basically you have at the center of a galaxy a supermassive black hole, and when you have infalling matter, if you drop 1 kilogram from far away into a black hole, the amount of energy that you can retrieve is phenomenal. It's like 20% of the breast mass. So there's a lot of energetics that are available in active galactic nuclei. Another thing that we're sensitive to are gamma ray bursts. Shown here are what is the model for the short duration gamma ray bursts, where you have two neutron stars colliding, and when they collide, you have a lot of energy available to produce gamma rays and other phenomena. We can study pulsar wind nebula, such as the Crab, where you have a region where you have magnetic fields, and where you have charged particles propagating through a region of magnetic fields, you can induce synchrotron radiation. So a lot of these objects should be studied with multi-wavelength, requiring many different observatories. So for instance, X-rays, gamma rays, even down to the optical and radio. Supernova remnants are another source of gamma rays that we can study with HAWC. And I had to throw in a cool video from NASA showing a nice artist conception of a neutron star ripping off the surface of another star, creating an accretion disk, and providing the energetics to produce gamma rays and high energy particles. Like I mentioned at the very beginning, one of the things that gamma ray observatories are interested in is looking for the signature for the acceleration regions for ultra energy cosmic rays. And another topic that can be addressed with gamma ray observatories and HAWC is the measurement of the amount of light in the universe that's been produced by various phenomena. So when you look at gamma rays being emitted from distant sources, as the gamma rays propagate through the universe, they get attenuated. By studying the energy spectrum, as we receive the gamma rays at Earth, we have some sensitivity to the amount of light along the path that the gamma ray traversed. And I'll talk a little bit more about that in a moment. HAWC can also study cosmic rays, since most of our petabytes of data will be cosmic rays. This is a measurement of the anisotropy of arrival directions carried out by Milagro in the top here, an ice cube. I will be showing you what we've recently done with HAWC. We can measure the energy spectrum of cosmic rays as well. And also, one of the graduate students here, Aaron Barber, is investigating the effect of coronal mass ejections on the flux of cosmic rays. I'll mention a few words about that. So, one of the benefits of looking at gamma rays is that they are not deflected by magnetic fields. So, if you're on Earth observing from the Veritas Observatory, HAWC, Fermi, if you're looking at the gamma rays, you're actually looking at where they came from. Whereas for the cosmic rays, especially the lower energy cosmic rays, their paths are deviated by the presence of magnetic fields. So once these particles reach Earth, they have to get through the Earth's atmosphere if you're observing from the surface of the Earth. And this is one of the reasons why you have NASA and governments spending many, many millions of dollars to put detectors in space. Because in this region, X-rays and gamma rays and ultraviolet are the direct propagation of those particles are blocked by our atmosphere. It's fortunate for us, I guess. Otherwise, we might not be here. So, even though the gamma rays themselves don't reach the surface of the Earth, you can still observe them by their effects left through the atmosphere. I'm going to be talking about these extensive air showers that both Air Cherenkov telescopes and ground array detectors use to measure the properties of gamma rays. So here's a cartoon showing a gamma ray entering the upper atmosphere, creating an extensive air shower, what I'll talk a little bit more about in a moment. The charged particles in that air shower emit Cherenkov radiation, or give off Cherenkov radiation, because the charged particles are traveling faster than the speed of light, and there's a phenomenon called Cherenkov radiation that's somewhat akin to a sonic boom. And the Cherenkov light can be detected by ground-based telescopes, and then thereby can measure the properties of the incoming gamma ray. So many detectors like Veritas, the future CTA, HESS, MAGIC, use this technique to measure the properties of the gamma rays. HAWC, on the other hand, is based on the ground. It observes the passage of charged particles that go through the detector element directly. This is a rendering of a simulation of an extensive air shower using the Corsica software that's used by, which is a standard used in the astrophysics community. This is basically an integrated view. What you would actually have is a surface of charged particles propagating at the speed of light that would hit the surface, and I'll talk a little bit more about how we can measure that in a moment. So extensive air showers, a few words about that. In the upper atmosphere, if you have a gamma ray or a proton or iron nucleus, it will slam into, or bremsstrahlung in the case of gamma rays, off of nuclei in the upper atmosphere. And those daughter particles continue doing that until the energy of the particles falls below some threshold energy, and then the air shower reaches a maximum and then subsides. So this shows you the number of electromagnetic particles as a function of radiation length for 100 GeV, 1 TeV, 10 TeV, 100 TeV particles. So for 100 TeV air shower, you would have about 100,000 particles at the maximum of that shower. If you're at 10 to the 18 electron volts, you would have 1 billion. You can describe the longitudinal development of these air showers with functions, and you can also describe the lateral distribution of the air showers with what's called the NKG function, which I'll discuss in a moment. Yeah, one thing I should point out is that hadronic showers are clumpier because you can have pions and muons that have high transverse momentum that move away from the core of the air shower and produce sub-showers that are far away from the main shower axis. So shown here is a video produced by some of the members of Veritas. It shows a gamma ray, a proton, and a carbon atom creating air showers. The altitude is indicated. Let's go back. So if you notice, the gamma shower is much more slender in comparison to a proton, and then the carbon is even more broad. These are all 400 GeV particles. So you can see that if you can measure the properties of the lateral distribution of the particles, you can distinguish between gammas and protons rather readily. And that's one of the things that we exploit to enrich the photon sample.
What's the time scale of this process that was just shown?
Those particles are moving at the speed of light, so.
Okay.
So the various techniques that are used to observe gamma rays, the most straightforward way is to get $1 billion and build a high energy physics experiment and put it into orbit. That one instance of that is known as the Fermi Glass Observatory. There's been several others, Swift, Batsy, a whole bunch. In this case, you can directly observe the gamma ray. You can sample the properties of the gamma ray exquisitely. You have very good energy resolution. The problem is that these detectors are small. So if you go into an energy regime where the flux is low, you're going to have to wait a long time to make measurements. So satellite-based detectors really can't measure or observe many particles above several tens, hundreds of GeV. On the ground, you have the advantage that you can access your detector site. You might have some difficulty. This is at 13,900 feet. It takes a day or two to acclimate sometimes. Some of us can just go up there and run. You have a guy in a suit in the front row. Actually, I observed do that. The imaging air atmospheric Cherenkov observatories, they are ground-based, of course, and they can intercept the Cherenkov light and actually have a rather large effective area because they can detect the gamma rays from a large region of the atmosphere. So this is a rather busy slide comparing the properties of satellite-based imaging Cherenkov telescopes and surface detector arrays. As I mentioned, the satellite-based detectors have a small effective area and therefore are sensitive to low energies. The imaging Cherenkov telescope and a large surface array have a relatively large effective area, nowhere near as large as high-res or telescope array. We're not looking at 10 to the 20 EV particles. You don't need to be sensitive to those fluxes. The advantage of a surface detector and satellite-based detector over imaging Cherenkov detectors is the field of view. So both the satellite-based detector and the surface detector are looking at a large fraction of the sky at any given time. The imaging Cherenkov telescopes have a narrower field of view of a couple degrees. In terms of identifying particles, a high-energy physics detector in space is relatively background-free. It can tag photons event by event. Imaging Cherenkov telescopes do a better job at rejecting hadronic background over surface detectors. Another advantage of satellites and surface detector arrays is that these two types can be on 24 hours a day, whereas imaging Cherenkov telescopes can only operate at night. These satellite-based detectors, as I said, cover low energies. Surface detector arrays go to higher energies. Some examples: Egret, Fermi, Agile are the satellite-based detectors. HES, Magic, Veritas, and someday CTA are examples of imaging Cherenkov telescopes. Argo, Milagro, Tibet, and HAWC are examples of surface detector arrays. So prior to building HAWC, there was a facility located near Los Alamos National Lab, known as Milagro. They utilized a large pond that was 60 meters wide, 80 meters long, 8 meters deep. It was located at 2,300 meters. They deployed 700 and some photomultiplier tubes, and they were able to achieve sensitivity to 100 GeV to 100 TeV gamma rays and cosmic rays as well, with an angular resolution of between 0.4 and 1 degree. This facility proved the capability of using water Cherenkov detection to perform gamma ray observations. Following Milagro, we built the HAWC Observatory on a nice mountain. Actually, it's in between two mountains, halfway between Puebla and Veracruz. The third highest peak in North America, Pico de Orizaba, is just adjacent to the site. The facility is about 150 meters on a side, and I'll go through more of the characteristics in a moment. The HAWC collaboration consists of a dozen or so universities from USA as well as Mexico. University of Utah, Udara, Dave Kita, myself, Michael Newbold, and Aaron. This was a photo taken from the collaboration meeting that was held here at the university a few months ago. Going from Milagro to HAWC, of course, typically when you do something later, it should be an improvement. So Milagro was located at 2,300 meters, which was at an atmospheric depth of about 700 or so grams per centimeter squared. HAWC, going to 4,100 meters, is sampling air showers closer to shower max at lower energies. So if you build your detector higher, you can sample lower energy air showers. So that was one of the main reasons for going to HAWC. We have a slightly larger area. We have a segmented detector, and that results in an improvement between gamma hadron separation, and resulting in an overall increase in the sensitivity over Milagro by about a factor of 15. We built the facility in a modular manner. We were building tanks. So as we were building, we were able to operate the fraction of the detector as it was coming online.
What energy shower was profiled there? Do you remember?
I don't know, actually.
Okay. It's okay.
You should tell me. I would guess it's about a TV or so. High altitude, that's great. There's an advantage, but we're on a volcano. Fortunately, HAWC is next to Pico de Orizaba, which is dormant, not extinct, but dormant. Popocatépetl. It's not Spanish, it's Nahuatl. It's an Indian language. This is located about 30 miles from Puebla, and it is active. But I don't think we have an issue at HAWC. The main design principles of HAWC is we utilize the Earth's atmosphere to convert gammas into extensive air showers. We sample the air shower at a depth of about 600 grams per centimeter squared for vertical air showers. If the showers are coming in at an inclined angle, we're looking at deeper along the shower development. Each one of these tanks, these water tanks, is a 7.3 meter diameter cylinder with about 4.5 meters of water. That's 180 some thousand liters, roughly 200,000 liters. Inside of each one of those tanks, there are 4 photomultiplier tubes that register the Cherenkov light that's produced by the charged particles as the charged particles traverse the water. We can measure the time, the arrival time to sub-nanosecond level. That's necessary to be able to reconstruct the arrival directions, which I'll talk about in a moment. Each one of these photomultiplier tubes produces a pulse that is read out by electronics that have been recycled from Milagro. I'll briefly describe that in a moment. So some more characteristics of HAWC. Here's a photograph from a drone. If you were to count the number of these cylinders, it would be 300. 294 of them are actually full of water. 6 of them were used for dealing with water, filtering, storing. Eventually we will fill those. To sort of get a sense of scale, Atlas, the Atlas detector at the LHC is 46 meters long. This is about 46 meters. The amount of water is 51,600 tons in HAWC. Atlas weighs about 7,000 tons. Fortunately, water is cheaper than sophisticated electronics. There's 181 kilometers of cable in HAWC, 3,000 kilometers in Atlas, so I'm glad I didn't have to cable Atlas. Sierra, so the location is 18 degrees above the equator, which gives us some access to the southern sky. We can see the center of the galaxy, but just barely. One of the reasons why we went to this location is the prior existence of the large millimeter telescope. It's a 50 meter dish that's sensitive to microwaves. There's a road, there's electricity, so we saved quite a bit by utilizing that pre-existing infrastructure. So each one of these tanks is commercially available. The one thing that I remember is that there's about 2,500 nuts and bolts that are used to bolt these together. So my Spanish is really horrific. but even when Alzheimer's sets in, I will still remember the phrase, "Más tuercas, por favor." More nuts, please. Inside of each one of these metal tanks, there's a waterproof bladder which contains the water and prevents the water from leaking out. Usually, there have been leaks, actually catastrophic. There was one catastrophic leak that almost wiped out cabling trenches. The biggest portion of the detector is water, lots of it. So each one of these tanks required 17 water trucks. Okay. So it's quite an endeavor.
Where did the water come from?
It came from a spring down at the bottom of the mountain. So they had to drive up about 2,000 meters.
How long does it last? What's the lifetime of the water?
The water, there's extensive treatment and it's sampled and monitored. It's hoped that it will last a long time, but we are monitoring it. And all of the water was treated extensively. We have a big facility up on the mountain to do water treatment.
What's the projected lifetime of the experiment?
At least 5 years, more than likely 10 years.
You get 10 years out of
or
DOE and that's about it.
That's the,
DOE will fund it for 10.
10 is a lot for.
Yeah, it'll last.
So we recycled about 900 previously existing phototubes from the experiment Milagro, and we added 300 additional 10-inch phototubes. We recycled electronics and some readout cards as well. Cabling. I should mention cabling because several of us suffered. The coax cables, fiber optics for calibration, and some signal cables for measuring for water depth sensor connections are all buried throughout the facility. Here at Utah, Dave Kita developed a technique to match the cable delays to better than 1 nanosecond, which is actually very useful. In theory, you can calibrate away any of these differences, but when we started taking data, all of the timing was already taken care of by having cables that were matched, and we were able to more easily, more readily see air showers because that was taken care of. Here are the bosses in suits. So the electronics, the phototubes produce pulses, and we have rather simple electronics that discriminate the pulses and then measure the time at the edges of the pulses, and all of this gets thrown into a farm of readout computers. If any of you are familiar with high energy physics experiments, you typically would select events, you would have hardware to form a trigger. This experiment basically records all of the hits, and in software using the computing, we can basically do our own triggering after the fact. The data rate is from each PMT about 10 to 20,000 hits a second. If you have 300 tanks, that adds up to about 500 megabytes per second coming out of the detector. What we store is about 10 megabytes per second, 2 terabytes a day, petabytes per year. We have internet, but that's a lot of data to get off the mountain. So we typically fill an array of disk, load it up in Arturo's truck, and he drives off to UNAM, and then eventually it hits the internet and gets copied to Maryland.
How long does it take to get back to the University of Utah?
The data is basically at Maryland. We don't
How
copy
long
all
does it take to get there?
a few days after it's
Getting to,
been
you know,
transported to UNO.
how
Okay.
often is it driven down the hill?
What?
How often do you drive it down the hill?
Typically every week. So to make sense out of all of these all of these observations, we need to model the aperture and sensitivity, the background rejection, our energy and angular resolutions, and we use the standard Corsica, Jayant tools that many of you are familiar with. So, as I showed in the second slide, the number of gamma rays compared to cosmic rays is rather small. So, ideally you would have some means of discriminating between photons and hadrons. And what you typically do is you look for clusters of energy deposition away from the main core of the air shower. So for proton, you see hits away from the core. And that's the result of these hadronic interactions where you have pions and muons carrying away energy from the central shower axis. So for photons, you typically see most of the energy deposited in a rather small area with few clumps outside of that. Now, of course, you have to have good timing because you're looking at megahertz of showers and muons hitting the detector. But if you look at an event, you can see that the space versus time gives you a plane. So you can easily tell that this other hit is not associated with that particular air shower. So it's not as at first I was worried of, wow, you got all these hits, you're always going to be finding clumps outside, but not if you look at what's consistent with a shower front. So using the detector simulation, we can evaluate what is the effective area of the detector. That's necessary to be able to normalize the number of events that you have to pull out the actual physical quantity of the flux. We also are interested in maximizing our hadron efficiency to reject protons and get a more pure photon sample. The energy resolution at about 100 GeV, we can basically measure the energy to a factor of 2. As you go to higher energies, it gets better. But again, using the tricks from Milagro, where instead of basically getting your energy spectrum by binning in energy, counting events, dividing by flux, if you do a fit to the overall energy spectrum, you can do a much better job. This is a plot that is a great advertisement for a project that Dave's working on, CTA. This shows you the sensitivity, that is the minimum flux in units of Crab. The Crab Nebula is sort of a standard candle. So you see here that the proposed CTA project covers a wide span of energy and is sensitive to dim objects. HAWC, which is now in existence, does a pretty good job compared to prior experiments, but I guess Dave uses a plot like this to sell CTA. Looking at the sky, there are regions where we have no sensitivity. So we're at 18 degrees latitude. We can't see the portion of the sky directly above the South Pole. So we have no sensitivity there. We have reduced sensitivity to the north, even though we can see the North Pole. but actually this is in galactic coordinates. Okay, so I better speed up. One of the main interests of HAWC is sensitivity to objects that go bump in the night and also bump in the day. The astrophysical objects that we're interested in, many of them actually do not emit at a constant flux. They're transients. For instance, a gamma ray burst, that's a huge transient. Since we're basically looking at a large fraction of the sky, we're monitoring a good portion, quite a large fraction of the time. Even though the gamma rays are attenuated as they cross the universe, we are sensitive to the most nearby distant objects, so we can hopefully see many of, actually we do see several blazars. One of the strong points of HAWC is its ability to look at a large fraction of the sky and therefore extended objects. So one of the things that we hope to be able to elucidate is the object known as Gaminga. There's some interest in that related to some purported measurements of positrons associated with possibly dark matter annihilation, but there might be a more mundane explanation associated with the astrophysical object Gaminga. So, as I mentioned many times already, HAWC is sensitive to diffuse, that is emission areas that are spread out over a large angle. For instance, the Fermi Bubbles, they're rather large objects, about the size of a Milky Way. And here is the image from Fermi. And if the emission spectra associated with whatever is causing these Fermi bubbles goes to high energies, after 3 years, HAWC should be able to see them. However, if the emission spectrum is cut off, we won't be able to see these objects because we're sensitive to higher energies than Fermi. We can't go down to as low an energy as Fermi. We're sensitive to dark matter annihilation. We can perform energy spectrum measurements, as I mentioned. We can perform cosmic ray anisotropy measurements. One of the thesis topics of HAWC that Aaron Barber is interested in working on is using HAWC to study the heliosphere by looking at the modulation of cosmic rays as a function of direction that might be related to the heliospheric magnetic fields modulating the flux of cosmic rays. So it's sort of like doing an X-ray of the solar system by looking at the flux as a function of direction and time. Michael Newbold is working on a measurement of the extragalactic background light by looking at the attenuation of the energy spectrum from sources that are distant. So HAWC exists now. It's completed. In February 2011, that's when everything started. That's when we got our money. In August of 2012, these first 30 tanks were constructed. We started taking data with those first 30 tanks. In August 2013, we had 111 tanks, and we started taking data with that collection of detectors. November 2014, HAWC was at 250 tanks, and March 15th of 2015, we finished off the 300 tanks. There is a plan, and there's actually funding to put what are called outriggers, small tanks around the main site. That's going to be useful for looking at air showers that are not contained. So this will allow us to see higher energy particles. The best way to see this facility, I guess, is by using a drone. You can see census scale. That was the Hegra detector. You can see some people over there. It's a rather large object. Not as large as the telescope array. So how do we reconstruct data? So we can measure the charge deposited in each of the tanks. So that basically gives us a measure of how much charge as a function of distance from the core of the air shower. And if this movie works, let's see if I can get it. Cannot play media. Wow, it worked before. Okay, so what this would have shown is hits being, tanks being hit as a function of time. And by looking at the time of hit of the tank hits, you can basically reconstruct a shower plane. So imagine that you have an air shower and the plane of charged particles is represented by my hand. As that plane hits the surface, the tanks on this side will be hit before the tanks over here. And by reconstructing the times, you can get the arrival direction to better than a degree. So it's kind of a really cool optical device. It's looking at the whole sky, yet it can still resolve the direction to better than a degree.
Are you limited by the clumpiness of the shower, the non-plane parallelness of it, or are you limited by the readout times?
More the readout times. Here's a couple of events. A likely cosmic ray event, and you see that there's clumpiness, and if you plot the effective charge as a function of distance from the center of the shower, you see a lot of scatter. This event is likely to be a gamma ray. It's much more compact, it's much more smooth, less clumpiness. So by doing statistical fits, you can get a measure of what is the probability of the thing being gamma ray or cosmic ray. So the first measurement that was performed by HAWC was the rather mundane observation of the moon. So shown here is a deficit in the flux of arrival directions of cosmic rays that is coincident with about a half a degree deflection from the direction of the moon. So this is actually kind of cool and very useful for calibration. You know the magnetic field between the Earth and the moon. You can measure the displacement of the shadow of the moon. That is going to be related to what is the energy distribution of the event you're looking at. So you can actually do an energy calibration by looking at the deflection of the moon.
I'm sorry. So, I'm sorry to understand. That's from the deflection. It's offset from the deflection of the shower in the Earth's atmosphere or over the course.
No,
of
the arrival. So you just basically do a sky map of the arrival directions of all of the particles. You will see a reduction in the flux.
Oh, that's okay.
Associated with the moon.
Those are cosmic rays. Those are not gamma rays.
Yeah, these
that's
are cosmic
understanding.
rays.
Okay,
Yeah, these
that
are
makes a lot
cosmic
more
rays.
sense.
Yeah.
Okay.
Oh, sorry. Yeah, in cosmic rays.
Okay.
Yeah, remember, the HAWC Gamma Ray Observatory mainly sees cosmic rays. So we also have a hardware-based calibration system where we have fiber optics and a laser delivery system that can provide light to the phototubes of each tank, and we can calibrate the charge response as well as the calibration using that system. One of the things that I missed from high energy physics when I joined cosmic ray physics was the ability to do a test beam. For gamma ray observatories, there is effectively what in high energy physics called a test beam. That is the flux of particles coming, the flux of gamma rays coming from the crab. It is not, it's constant most of the time. It used to be believed to be a standard candle. It's not, it does exhibit variability now, but it still can be used as a test beam. You know that you should see stuff from there. Okay? So Milagro, after 8 years, was able to see this little blip, excess of photons above the cosmic rays. Of course, you can do cuts to reduce this. So 17 sigma in 8 years. HAWC, in 150 days, sees the crab with 38 sigma significance. If you make strong cuts, you can see basically a pure photon sample. 25% efficiency for photons, but you have to throw away 9,999 out of 10,000 events to get that sample. So if you go to higher energies, you can also increase the signal, but also the background goes up as well. So this looks like a significant signal, but the significance is actually lower than that. Go back to plus one on Gaussian statistics. This is not a measure of the spectrum, energy spectrum of the crab, but it does show you the number of events, the excess number of events per day as a function of the number of hits seen by the detector, which is a proxy of energy. You can do fits to get to extract the energy spectrum from that. So HAWC is basically complete. We're now doing science. At the 34th International Cosmic Ray Conference that was held a few months ago, there were 31 contributions describing extragalactic physics, galactic physics, cosmic ray physics, and some of the results I'll quickly show here. The gamma ray significance map, you see in galactic coordinates, you see the galactic plane, the Crab Nebula, Dominga, some AGNs, Markarian 501, Markarian 421. You can do fits to identify point sources in this rather crowded area, the galactic plane. And then you could subtract the point sources to try to evaluate the diffuse emission in the galactic plane. We are seeing sources such as the HES sources in the galactic plane. We have seen Dominga, and this is an illustration of the fact that Dominga is a diffuse source. If you treat it as a point source, this is the significance map that you see, but if you allow the source to be extended, you see that the significance increases. Dominga is several times the size of the moon. Dave could actually give you a rather wonderful description of Dominga. Supposedly we are inside of Dominga. Shock front passed many millions of years ago. Another thing that HAWC is capable of doing is monitoring fluxes as a function of time. So this is from HES and HEGRA. flux versus time for an AGN, and you see there are times where there's like an outburst of activity. And HAWC is now monitoring the sky for such activity. So here you see the flux versus time for Markarian 421, Markarian 501. There's statistical fluctuations that aren't really indicating a burst. We can monitor the crab as a function of time. We can also, as I mentioned earlier, we can measure cosmic ray arrival directions, and there does appear to be an anisotropy. There's several regions that indicate an excessive flux, and if you do a power spectrum fit, you see that there's definitely a deviation from isotropy. One of the main purposes of HAWC is to alert other detectors. So we've developed a lot of agreements with many of the other currently operating gamma ray observatories where we share information. So for instance, if HAWC sees something, we can send a message to Veritas to go and look at that fraction of the sky.
So you must be looking online or something.
Yes,
You don't have to wait 2 weeks to get.
that's right. Right. So for instance, gamma ray burst, there's online searches for that. The future of HAWC, well, we finished building it, so we want to build more. We've actually, Los Alamos has gotten some money to build an array of outrigger tanks that'll be useful for detecting whenever an air shower spills outside of the main detector site. Some of our collaborators are interested in building another instance of HAWC in the southern hemisphere to cover the whole sky. That's it. Too much. Any questions?
What is actually the physics behind these bubbles that come out of our galaxy, these Fermi bubbles that you refer to?
One possible, one intriguing explanation is that is gamma rays being emitted from dark matter annihilation.
And why is that dark matter? Is there any hypothesis why this particular distribution then evolved?
I'm not aware of it, but I'm sure there's a theoretical model that can describe it perfectly.
There are more canonical explanations about the magnetic field that constrains the electrons, and they bounce around, and so they're still trying to figure it out, but there's a lot of different explanations.
I mean, it's consistent with all of these other AGN-like models where you've got the galactic plane, and then you've got jets shooting out. So you've got an accretion disk, and you've got activity coming out.
But you wouldn't have a dark matter jet, or would no? Right, that's why if it's due to dark matter, why is this distributed?
No.
So your energy measurement for a photon shower must be a little bit indirect because you're past X max and you have some attenuation. Milagro showed a bunch of those curves that you used to estimate how to soft do it.
So what we observe is number of hits, charge deposition, and you can infer energy event by event if you make assumptions. We are sampling at a certain depth. We're not measuring the whole shower calorimetrically like the fluorescence detector, but you could do fits where you model what is the expected response for a distribution of events. So we can estimate energies event by event, but the estimation is poor because there's a lot of stuff that's not under our control.
So what is the size of that uncertainty of the estimate?
100% for 100 GeV.
So you're looking at a huge field of view, and you're doing these like reconstructions by reconstructing the plane in which the charged particles are at. Does pileup of events ever become a problem, or is it too low of a rate?
The rate's high, but it's not, I haven't seen a problem.
Okay.
Basically, if you look at the event time as a function of position, if you were able to just basically take a snapshot of where the future hits are coming from, you can basically see that there's a lot of particles in a plane, and then there's stuff scattered about.
So you can discriminate.
I mean, there is a chance that you get
Yeah.
junk inside of your shower plane
But
as
you
well.
kind of discriminate one shower from.
Right, but it's not that crowded.
Just curious, I mean, it doesn't seem like, at least, you didn't talk about, like, when we hear about the TA tale about, over time, right, we gather a lot more statistics, so if you're looking to measure the shape of the flux curve, that's important. Here you didn't really talk about things like that, but are there things that improve over time, like, your Monte Carlo simulations, which I suppose go into sort of differentiating between cosmic rays and gamma rays? I mean, does something improve over time as you
Yeah.
gather more statistics? And
Yeah, well, if you're looking at gamma rays from sources over this huge background of cosmic rays,
So you're,
the
okay.
significance improves with time.
In terms of like the where the sources are, basically nailing that down.
The significance of each source will increase with
Yeah.
time.
And then, but do your Monte Carlo, I mean, you talk about, the challenge of separating, being able to differentiate between a cosmic ray shower and, how it's clumpiness, and, and you showed sort of those two curves that compare. And do you use Monte Carlo to sort of give confidence levels on whether you actually have a cosmic ray shower or a
Well, you can use
gamma ray
Monte
shower?
Carlo to help develop the reconstruction tools. You can use Monte Carlo to estimate your resolution and estimate the efficiency for rejecting hadrons. So, yeah, I mean, you use Monte Carlo
And
to guide.
and do those and is the Monte Carlo refined and get tighter and tighter over time, or is that something which is just kind of what it is?
The reconstruction techniques would get better, but Monte Carlo, somewhat.
Yeah.
The more events you have in the point source, then
So-
you have the larger number of known photons you have.
Right,
if they're in the point source, so you can refine the concepts.
So you mentioned the hotspot. How does that correlate with what was seen by TA? And why would there be a correlation if you're looking at much lower energies?
I remember looking at this in detail when they announced their thing. It's not really correlated.
Marcari at 421 is inside the hotspot. So it's probably too far away to be the certain source.
Hotspot's really big.
It's not really spot.
The hotspot was not counted as if it was mostly cosmic rays.
It's all cosmic rays.
So, yeah, so at lower energies, it'd be more magnetic.
These are above 57 EeV, the hotspot.
Yeah, HAWC is looking at much
Yeah,
lower
I know, so
energies.
you would expect more magnetic deflection, less
Right.
less directional.
So it's going to be spread out. Those hot regions in the cosmic ray anisotropy of HAWC, I don't know. We're looking at various explanations, but it's not clear at all.
It's probably something very local.
I mean, it actually sort of motivated maybe Aaron and I to look at the heliosphere.
If you look at the magnetic field, it couldn't possibly be very far away because it just gets scattered too much, so it has to be pretty local. It's quite different than the ultra high energy cosmic ray one.
So what happens when these photomultiplier tubes break, or do they even break, or is this so rare? Can you climb into these water bags and?
Well, yeah, there's rather sophisticated methods, mechanical methods using strings and pulleys and whatnot. I haven't been involved. My hands shake too much.
But you can pull them out.
But you can pull them out.
Mm.
Yeah, yeah, you don't have to get a wetsuit and go in, but they're connected by strings and pulleys. And there's a collection of tools that have been developed just for this. It's probably equivalent to being good at fair games.
Wait, how many gamma ray-like events do you collect per day?
Good question.
For anything?
How long would it take to get the crab pulsar? Do whatever sigma is.
Supposedly we're supposed to get in theory we're supposed to get 5 sigma a day. And if you limit the number of cosmic rays from that region, it's order thousands, and you're getting millions of cosmic rays from that small region of the sky. So to get 5 sigma, what do you have to get? So you have I'm getting a brain freeze right now.
The numbers about right that you said. The crab gives you, for something the size of Milagro, about 2 or 3 gammas per minute. So if you multiply that, you get a couple thousand per day.
So yeah, 5 sigma. I mean, you can calculate it. It's a very definite number.
For example, how long did it take to get the picture you have shown for the shade of the moon?
That was about 100 some days with a smaller detector. With a smaller detector.
Okay.
Yeah, we're just starting. But for instance, we write out little snippets of raw data, and in 250 milliseconds, there's like 7 million hits. So I'm doing mundane things like I can actually see stop muons. I can calculate the muon lifetime. If the grad lab experiment doesn't work, I can use data. So yeah, Aaron jokes that I'm doing particle physics with all muon lifetime. Any other questions?
I keep forgetting the name of the scattering model, but Sintras or Sintra something? Sintras? The model that gives you the
Corsica?
Corsica. Does the as the species are lower and lower energy, is the scattering assumed to be dramatically different, or is it kind of this directional scattering over the depth of the atmosphere? Is the scattering
Corsica incorporates many of the high energy physics models and different energy regimes, and you can actually swap out QGS jet, QGS CO2, and then for detailed simulations of particle detectors, you use this other thing called JAION. So one of the things that I want to find out is whether JAION actually models the muon decay tanks properly.
So is it small? The scattering is a small number. It's not a large number that's formulaically changed for every energy, but it's something that a small number. So
You're talking about multiple scattering. What is the dispersion?
yeah, multiple scattering after a species, like when one particle has a different energy, is the directional part of the scattering assumed to be wildly different, or is it kind of just been and say, well, they roughly have this energy, so we have the same?
Well, if you look at the high energy parts of the showers, the scattering, especially for the electromagnetic showers, is it's large in terms of my size, but in terms of the length of the shower, it's in terms of angles, it's not that great.
I'm not sure Corsica does any multiple scattering. JAION does
atmosphere, it's not as
Well, you
important.
would think it would, but I don't ever, I don't remember reading anything about it ever in the manual.
This is getting very tight.
Yeah.
Thank you, Wayne.
Here, through the budget, was it reconstruct the facility where you come from, or you just go to the pilot, right?
Actually, the town wants it.
Oh, they want it. Oh, okay.
Yeah.
Okay.
You two are just here. Should we meet next week sometime?
Oh, okay. Right.
Okay, so then I will ask Heidi.
She still has my calendar.
She has my calendar too.
Okay, all right.
Good. Yeah, I'm around.
Cool. See you.
Actually, the fun thing was Fermi Bubbles. So, you go way back before the Fermi Bubbles existed. You go back to 1990 when I first got here. People argue about where they find these cosmic rays come from.
Mm.
The guy, Randy Jacobi,